National 4-5 waves, refraction. In this section, we're going to look at the definition of refraction, characteristics of refraction, lenses, and that is the uses of refraction. Our learning outcomes: I can state that refraction occurs when waves pass from one medium to another. I can describe refraction in terms of change in wave speed, wavelength, and direction. I can identify the normal, incident ray, refracted ray, angle of incidence, and angle of refraction on a diagram. Refraction is the change in speed of light when passing from one medium, material, to another, for example, air to glass. When light enters a more dense medium, it will slow down, just as you would slow down if you were traveling on a flat path and all of a sudden were traveling through water. For example, the speed of light in air is approximately 3 times 10 to the 8 meters per second. However, the speed of light in glass is approximately 2 times 10 to the 8 meters per second. Refraction through a rectangular block. When light enters the glass block from the air at 90 degrees to the surface, it passes straight through in a straight line. Now at this point, we can't see refraction, but refraction has taken place. Light travels slower in the glass than it does in the air, and that is the definition of refraction. Note, the frequency and so the color of the light does not change as it passes through the material, but the wavelength will be decreased. If the light travels at an angle to the normal line being drawn at 90 degrees to the surface of the block, then we'll see the light changing direction as well as changing speed. And this change in direction will occur at the boundary between the air and the glass. Here's our incident ray, refracted inside the glass, and then refracted again as it exits the glass. So the light changes direction again when exiting the block from the glass to the air, just as it did when it entered the block going from air to the glass. Should note that these two lines here are parallel to each other. Looking at this diagram again, we can note some key features. The angle between the incident ray and the normal is called the angle of incidence. The angle between the refracted ray and the normal is called the angle of refraction. And we see angles of incidence and refraction also from the boundary going from the glass to the air. We can note that when moving from the less dense air to the more dense glass, the angle of refraction is less than the angle of incidence. So light refracts towards the normal when going from a less dense to a more dense medium. However, when the light is moving between glass, a more dense material, to air, a less dense material, we see that the angle of incidence is less than the angle of refraction. And so light refracts away from the normal when going from a more dense material to a less dense material. The triangular prism. We've seen how light behaves going through a rectangular block, and now we can use our knowledge of how light changes direction going from different densities of mediums in order to predict the path of light going through a different shape. This is the triangular prism. We see an incident ray going into the surface, and we draw a normal. We can predict that the light ray will be refracted towards the normal because we're moving from a less dense medium to a more dense medium. Then we draw another normal, and we can predict that the ray of light will now refract away from the normal because we're moving from a more dense medium to a less dense medium. We should note that this is monochromatic light, that is light of only one color. And as we'll see in the next slide, white light behaves a little differently. When white light enters the boundary between glass and air, it starts to split into its component colors: red, orange, yellow, green, blue, indigo, and violet, and then continue to split as it's refracted out of the prism. White light is made up of a series of other colors: red, orange, yellow, green, blue, indigo, and violet, or Roy G. Biv as it's often remembered. We can see from the animation here white light entering the prism and then being split into the component colors. Explanation. As we heard previously, the color of light is determined by its frequency, which does not change when it's being refracted. Each frequency, or wavelength of light, refracts by different amounts. Violet light refracts the most, and red light refracts the least. When white light refracts through a prism, it's split into its component colors, creating what is known as a continuous spectrum. Now this is how rainbows are formed. The top of a rain droplet looks like a triangular prism. White light refracting through the water droplets in the air after the rain creates the rainbow. But unfortunately, the rainbow song is wrong. Here's a different one to help you remember the colors of the continuous spectrum.
John, tell us another story.
No, don't make me tell any more stories.
Please regale us with another story.
I don't have any more stories. Oh, okay. In olden times, my father would help me remember the sequence of the color spectrum by telling me the story of a magical elf named Roy G. Biv. He even wrote a song about it. And the name of the song is Roy G. Biv.
R is for red, O is for orange, Y is for yellow, and G is for green. B is for blue, I for indigo, and B is for violet. And that spells Roy G. Biv. Roy G. Biv is a colorful man, and he proudly stands at the rainbow's end. So you'll Roy G. Biv is a colorful man, and his name spells out the whole color spectrum. Roy G. Biv is a colorful man, and he proudly stands at the rainbow's end. Roy G. Biv is a colorful man, and his name spells out the whole color spectrum. You'll never see a unicorn, but you'll see a rainbow. And inside every rainbow is the spectrum of light. You'll never see Roy G. Biv, but he's inside the rainbow. 'Cause inside every rainbow is the spectrum of light. R is for red, O is for orange, Y is for yellow, and G is for green. B is for blue, I for indigo, and V is for violet. And that spells Roy G. Biv. Roy G. Biv is a colorful man, and he proudly stands at the rainbow's end. So you'll Roy G. Biv is a colorful man, and his name spells out the whole color spectrum. Roy G. Biv is a colorful man, and he proudly stands at the rainbow's end. Roy G. Biv is a colorful man, and his name spells out the whole color spectrum.
Now hopefully you'll remember Roy G. Biv. Convex and concave lenses. When light enters a convex lens, it's brought to a focus point, as can be seen in the diagram. Light enters in parallel lines, and as it strikes the surface of the lens, each of the rays are refracted to a single point, which we call the focus point. This is why this lens is sometimes referred to as a converging lens, because the light converges onto one point. When light enters a concave lens, it's spread out. We often remember the name concave because of the caved-in shape of the lens. Again, light enters in parallel lines, but then is spread out as it exits the lens. And this is why this lens is sometimes referred to as a diverging lens. Convex and concave lenses are often used to correct sight defects, and these are what's inside the glasses that people wear.
When I was 10 years old, I realized that I couldn't see objects that were far away clearly. So I went to the doctor, and the doctor prescribed me spectacles. And I've been using a pair ever since. Now, if you don't use spectacles yourself, I'm pretty sure you'll know someone who does. But have you ever wondered about how spectacles work? Well, I have a setup here that might help us understand. The first thing we need to know is that spectacles are just a pair of lenses. And these two transparent pieces of plastic, they're lenses. And there are two main types of lenses. The first is a converging lens. Over here, I have a biconvex converging lens. Now look at what happens when I place it in the path of these rays. You see that? The rays hit the lens and then they get converged to a point. And hence the name converging lens. The other type of lens is a diverging lens. And over here, I have a biconcave diverging lens. When the rays pass through the lens, they get diverged. If you look closely, you'll notice that they look like they are emerging from a point behind the lens. Now, the human eye basically consists of two main parts: a biconvex converging lens, which we call the eye lens, and a screen, which we call the retina. So let's try to simulate the human eye over here. So let's say that this biconvex converging lens plays the role of our eye lens. Okay? And I have a screen over here that's going to play the role of our retina. Now, if you look closely, this is what happens in the case of a healthy eye. The rays come off objects and then the eye lens converges those rays to a point on the retina. And therefore, this person sees a clear image. But then, sometimes there are defects. And the most common defect is called nearsightedness or myopia. In this case, the person can see objects that are close by clearly, but far away objects appear blurry to them. When this person looks at objects that are far off, those rays get converged to a point in front of the retina, like this. And therefore, he ends up seeing a blurry image. Now, this can happen for a variety of reasons. Maybe the eyeball itself is too large, or there's some kind of issue with the eye lens. Now, how would you correct this? As you can see here, it's happening because the rays are getting converged a little too much. So you need to negate that. One way to do that is to introduce a diverging lens. Now watch. Here I have a biconcave diverging lens. Look at what happens when I place it in front of the eye lens. Do you see that? The moment I place the biconcave lens, the rays now intersect on the retina. Now, this is because the incoming rays are first diverged by the corrective lens, and then the eye lens can further converge those rays onto the retina. So now, this person can see a clear image of those far off objects. So this is why a person with nearsightedness requires spectacles with diverging lenses. So the other type of common defect is called farsightedness or hypermetropia. And this generally occurs when people get a little older. So what happens in this case is that when they see objects that are close by, they appear blurry, and objects that are far off appear clear. Now, when you look at their eye, this is what happens. So when these people look at objects that are close by, those rays get converged to a point behind the retina, and therefore this person ends up seeing a blurry image. Again, this can happen maybe because the eyeball itself is too small, or maybe there's some problem with the eyelids. But how would you correct this? As you can see, the issue is happening because the rays are not getting converged enough. The eye lens requires a helping hand to converge the rays further. So therefore, we introduce a converging lens. So over here, I have a biconvex converging lens. Look at what happens. You see that? The moment I bring the lens, the rays now intersect on the retina. And this is happening because the incoming rays are first converged by the corrective lens, and then the eye lens can further converge those rays onto the retina. And therefore, this person can now see a clear image of those objects that are close by. So this is why a person with farsightedness requires spectacles with converging lenses.
Make your child fall in love with learning. Download Byju's, your personalized learning app.
Total internal reflection, TIR. Total internal reflection occurs when light is reflected after entering a lens. The total internal reflection can only happen if the angle of incidence, the angle between the normal and the incident ray, is greater than what is known as the critical angle. The principle of total internal reflection is used for the transmission of light through optical fibers, as opposed to electrical signals through a copper wire. The main advantage of an optical fiber is that many signals can be sent simultaneously through a single fiber. This increases bandwidth, which is why optical fibers are used for broadband internet connections. In diagram 1 here, we can see that the incident ray is at an angle which is less than the critical angle, and so light is refracted out of this semicircular block. In diagram 2, the light is entering the block at the critical angle, and so light is refracted out at 90 degrees to the normal, or along the surface of the block. In diagram 3, the angle is greater than the critical angle, and so total internal reflection occurs. Summary. Refraction is the change in speed of light when passing from one medium to another. When we pass from a less dense medium, such as air, to a more dense medium, such as glass, light slows down, and vice versa. Lenses of different shapes are used to refract light. We looked at the rectangular lens, the triangular prism, the convex and concave lens as different options on how to refract light in different ways. Prisms can be used to split light into the spectrum: red, orange, yellow, green, blue, indigo, and violet. And that's because white light is comprised of different frequencies of light, and each frequency refracts by a different amount. Convex and concave lenses can be used to correct sight defects. Total internal reflection is used to transmit light waves in optical fibers.